You know how sometimes you really want to get your head around something complex, but without wading through tons of jargon?
Yeah, absolutely.
Well, consider this your shortcut, your fast track to understanding a concept that's frankly everywhere right now and could genuinely reshape our future. Artificial general intelligence, or AGI.
Exactly. And we spent some time with the source material, specifically AGI v3 1.pdf, to really pull out the core stuff for you.
Okay.
We're talking about, what AGI really is, how the idea even developed, the theories behind it, what it might actually do.
Maybe citing possibilities.
Right. But also the really important ethical side, the societal impact, and where the research is headed right now. Basically, the mission here is a clear, solid understanding.
Perfect. So let's jump right in. The big question first. What exactly are we talking about when we say AGI?
Okay, so think of AGI as the ultimate goal in AI research. It's about creating machine intelligence that has the same kind of broad cognitive abilities that, humans have.
Meaning it can think and learn like us?
Essentially, yes. A system that can understand new information, learn from it, and then apply that knowledge across a whole unlimited range of different tasks, performing them at a level comparable to a human.
So it's way beyond just like a computer being incredibly good at chess or Go.
Precisely. That's narrow AI or specialized AI. It excels, maybe even surpasses humans, but only in very specific domains like chess or recognizing faces or transcribing speech. AGI would possess intellectual versatility.
Versatility, meaning it can adapt.
Exactly. It could tackle completely new situations, things it hasn't been explicitly trained for, without needing someone to reprogram it for every new challenge. Imagine a truly flexible, adaptable intelligence in machine form.
And what kind of abilities are we talking about? Is it just pure logic, number crunching?
Oh, it goes much, much further than that. AGI isn't just about problem solving. It would likely involve creative thinking, generating genuinely new ideas, and understanding and responding to emotions, emotional comprehension. Plus, metacognition, which is basically the system being aware of its own thinking process.
Thinking about thinking.
Right. And some researchers even speculate that true AGI might involve developing consciousness or self-awareness, though that's a whole other deep topic.
That sounds incredibly ambitious. What fields are even tackling this? It can't just be computer science, right?
Not at all. It's fundamentally interdisciplinary. You absolutely need computer science for the algorithms and models. But you also need cognitive psychology to understand how our minds work, how we learn and reason.
Makes sense.
Neuroscience is crucial for insights into the brain, the biological hardware of intelligence. And even philosophy of mind plays a big role, helping us grapple with those fundamental questions about what intelligence and consciousness actually are.
Okay, so bringing it down to a more maybe technical level, what would an AGI system actually need to be able to do?
Technically, achieving AGI likely requires breakthroughs in several key areas. We're talking really advanced unsupervised learning without needing everything pre-labeled.
Learning on its own, basically.
Right. Transfer learning is another big one. The ability to take knowledge from one area and apply it effectively to a different one. Think about how a chef can adapt techniques to totally different ingredients.
Okay, yeah.
Then there's causal reasoning, understanding cause and effect, not just correlation. Robust, common-sense knowledge representation, capturing all that everyday stuff we just know about the world.
Like don't step off a cliff, that kind of thing.
Exactly. And integrated cognitive architectures, systems that can smoothly combine different kinds of learning, memory, and reasoning. Some theories also point to the need for an internal world model, a kind of simulation of the environment it uses for planning and adapting.
This really does bring up some massive questions, doesn't it? I mean, can we actually replicate something as complex as human intelligence in silicon?
Absolutely. The pursuit of AGI forces us right up against these fundamental philosophical questions. Is intelligence, at its core, computational? Can something like subjective experience, consciousness, actually emerge from just running algorithms, however complex? These aren't just side issues. They're central to the theoretical work.
You mentioned narrow AI again. Can we really pin down the key differences? How is what we have now not AGI?
The contrast is pretty stark when you look closely. Narrow AI, despite being incredibly impressive in specific tasks, operates within really rigid parameters. It's fantastic at what it's trained for, but it lacks genuine understanding and adaptability.
So it doesn't get it.
Pretty much. It relies on statistical patterns it found in its training data and behaviors programmed to achieve a specific goal. It doesn't truly comprehend the concept it's dealing with. Think of narrow AI like A highly skilled specialist surgeon, amazing at one procedure, but you wouldn't ask them to, say, fly a plane. AGI aims to be the polymath, the adaptable generalist.
Can you give a really clear example of that limitation?
Sure. Take an AI system trained to recognize cats in photos. It might be incredibly accurate. But show it a weirdly drawn cartoon cat, or a cat in a very unusual context it hasn't seen before, and it might completely fail.
Because it doesn't understand catness.
Exactly. It doesn't grasp the underlying concept of a cat in the flexible way a human child does. It just knows the patterns associated with cat in its training data.
So it hits a wall with novelty, with edge cases?
Precisely. Narrow AI struggles when faced with situations that deviate even slightly from its training. It also has no concept of its own limitations. It doesn't know what it doesn't know, so it won't ask for clarification if something is ambiguous.
Unlike a person who'd say, wait, what do you mean?
Right. And crucially, it lacks that ability for true abstraction and generalization, taking knowledge learned in one context and applying it insightfully to a completely different one. That cross-domain transfer is a hallmark of what we expect from AGI.
So those really advanced language models we see now, they can generate incredibly fluent text, but you're saying they don't really understand it.
That's the current consensus, yes. They are phenomenal pattern matchers and predictors based on the massive amounts of text they've ingested. They can mimic understanding, even perform some reasoning tasks based on those patterns. But they lack true grounding in the real world. They can generate factually incorrect information, hallucinate details, or even contradict themselves within the same paragraph without any awareness of the error. They're manipulating language patterns, not concepts with real meaning.
That really underscores the gap. We're good at specific tasks, but general intelligence is another beast entirely.
It is a significant leap. Current deep learning methods are fantastic at pattern recognition from vast data sets, but they still generally struggle with things like robust abstract reasoning, long-term planning, and incorporating common sense knowledge flexibly. Bridging this gap might need more than just bigger models and more data. It might require fundamentally new computational paradigms.
This all sounds incredibly futuristic, but you mentioned philosophy. The idea of intelligent machines, or artificial minds, it's not brand new, is it?
Oh, not at all. The roots go way back, long before computers even existed. You can find early philosophical explorations in Western thought. Think Aristotle analyzing logic, or Descartes grappling with the mind-body problem.
And in Eastern traditions, too.
Absolutely. Buddhist philosophy, for instance, has deep inquiries into the nature of consciousness in the mind. These ancient thinkers were essentially laying the conceptual groundwork, asking, what is thought? What is the self?
So these fundamental questions have been with us for millennia.
Exactly. And then fast forward a bit, logic started getting formalized. People like George Boole in the 19th century developed algebraic systems for reasoning. Later, Frege and Russell developed symbolic logic, giving us precise ways to represent knowledge and inference. These were crucial steps.
Tools for thinking about thinking, in a way.
You could say that. They provided the formalisms that would later underpin computational approaches. These early explorations established the key questions, while the later Dartmouth workshop, which we'll get to, really kicked off the computational pursuit.
Right, and then came the computing pioneers like Turing.
Exactly. Alan Turing was absolutely pivotal. His 1950 paper, Computing Machinery and Intelligence, is still a landmark. He proposed the famous Turing test as a benchmark for machine intelligence.
The imitation game.
Right. But he also engaged deeply with the philosophical questions, could a machine truly think? Could it be conscious? Around the same time, Norbert Wiener was developing cybernetics, studying feedback systems and goal-directed behavior in both biological organisms and machines.
So they were laying down the theoretical foundations, asking those core questions we're still grappling with.
Precisely. What is intelligence? Is thought computation? How does the physical stuff, the hardware, whether it's neurons or silicon, relate to cognitive abilities? These questions were there from the start.
And when did AI become, an actual field of research?
The generally accepted birth date is the 1956 Dartmouth Summer Research Project. This was a workshop that brought together key figures who coined the term artificial intelligence and set out some incredibly ambitious goals. Things like creating machines that could use natural language, form abstract concepts, solve problems currently reserved for humans, and even improve themselves, really aiming high from day one.
That sounds wildly optimistic. Did progress match that initial vision?
Not exactly smoothly. The history of AI is often described in terms of AI springs. periods of great optimism and funding followed by AI winters, where progress stalled, promises weren't met, and funding dried up.
Right, I've heard about the AI winter.
Yeah, the 60s saw some early successes with symbolic AI, like programs that could play checkers or solve logic problems and things like Eliza the chatbot. But the limitations of purely rule-based systems became apparent pretty quickly.
They were too rigid.
Too brittle, yeah. Then in the 70s and early 80s, we saw the rise of expert systems programs designed to capture the knowledge of human experts in narrow domains, like medical diagnosis with MYCN. They had some success, but again, they were very limited to their specific area and couldn't handle unexpected situations well.
And neural networks came into play then, too.
There was a resurgence of interest in connectionism, neural networks inspired by the brain, in the 80s. But the computational power available back then really limited what they could achieve. They couldn't handle the scale needed for complex problems.
So lots of starts and stops, different approaches rising and falling.
Definitely. A really pivotal shift happened in the late 90s and early 2000s. Statistical machine learning techniques really took off, combined with Moore's law providing much more computing power. Algorithms like support vector machines, decision trees, probabilistic models, they became much better at learning from data.
And that set the stage for the deep learning explosion we're living through now.
In many ways, yes. That combination of algorithmic advances, massive data sets, and powerful hardware, especially GPUs, fueled the deep learning revolution. But even with all this incredible progress in narrow AI, that original Dartmouth dream of general intelligence, AGI, still remains the ultimate, albeit elusive, goal.
Okay, so we have a clearer picture of what AGI aims to be and its history. Let's talk potential. What could AGI actually do if we achieved it? What are the applications driving all this research?
Well, the potential applications are frankly staggering, almost science fiction territory, but grounded in real possibilities. Take scientific research, for example.
Okay.
An AGI could potentially function as an autonomous research partner, or even an autonomous scientist. It could sift through vast amounts of data, formulate novel hypotheses, design experiments, interpret results.
Way beyond just data analysis.
Exactly.
Yeah.
And crucially, it could integrate findings across completely different scientific fields. Imagine trying to tackle massive, complex challenges like climate change, or developing cures for diseases like Alzheimer's, or achieving sustainable development. An AGI could potentially accelerate progress dramatically by connecting dots humans might miss.
That alone is a huge potential impact. What about more day-to-day areas like healthcare?
In healthcare, AGI could go far beyond current AI, which might help diagnose specific conditions from scans. An AGI could provide truly holistic, personalized patient management.
How so?
By integrating everything a patient's entire medical history, their genetic makeup, lifestyle data from wearables, environmental factors, even social determinants of health. It could develop dynamically adapting, personalized strategies for prevention, treatment, and long-term wellness, constantly adjusting based on new data and medical knowledge.
And education. You mentioned personalized learning earlier.
Right. Imagine an AI tutor that doesn't just deliver content, but truly understands each student's individual knowledge level, their learning style, their interests, maybe even their emotional state. It can engage in Socratic dialogue, identify subtle misunderstandings, dynamically generate customized explanations and exercises, offering a level of personalized support that's impossible in today's classrooms.
It sounds like AGI could fundamentally improve so many aspects of our lives.
Absolutely. Think about transportation and logistics, too. Optimizing global supply chains, managing autonomous vehicle fleets dynamically to respond to real-time traffic and demand, maximizing fuel efficiency, minimizing delivery times. The complexity is immense, perfect for an AGI's capabilities.
You mentioned earlier that AGI isn't just another tech advance, but a fundamental paradigm shift. Can you unpack that a bit more?
Yeah, I think comparing it to things like the invention of writing or the printing press or the Industrial Revolution helps put it in perspective. AGI, if realized, would be a transformation on that kind of scale. It introduces a non-human intelligence capable of matching or even exceeding human cognitive abilities across many domains.
That's a profound thought. How does that impact our view of ourselves philosophically?
It directly challenges long-held notions of human exceptionalism. If machines can genuinely think, reason creatively, maybe even possess consciousness, where does that leave human uniqueness? It blurs the lines we've drawn between human and machine, raising deep questions about identity, personhood, and our place in the universe. The core ethical challenge here is huge. How do we build something so powerful and ensure it aligns with human values? That's unprecedented.
And the practical side. Jobs, The economy.
Socioeconomically, the disruption could be immense. Previous automation waves mostly affected manual labor or routine cognitive tasks. AGI could potentially automate much more complex cognitive work, including roles currently considered high-skilled professions.
So potentially widespread job displacement.
That's a major concern. It could require a radical rethinking of work itself, how we value contributions, how resources are distributed. Models like universal basic income might become necessary discussions. Traditional employment might become unsustainable for large parts of the population, forcing us to devise new social contracts and economic structures.
Which leads directly to questions of governance. How do you manage something like this?
Exactly. Our current legal and regulatory frameworks are, frankly, unprepared for AGI. We'd need substantial reconfiguration to address issues like accountability, who's responsible if an autonomous AGI causes harm. How do we maintain control? How do we ensure alignment with diverse human values? How do we guarantee equitable access? It demands innovative regulatory thinking and almost certainly significant international cooperation.
But it's not all dystopian risk, right? You mentioned cognitive partnership.
Absolutely not. The potential for synergy is enormous. Imagine humans and AGI working together, combining our strengths. AGI could amplify human creativity and intellect, helping us solve problems faster, make new discoveries, create new forms of art. It could massively boost our collective intelligence.
So augmenting human capabilities, not just replacing them.
That's a much more constructive and potentially more likely way to look at it. A future where AGI acts as a powerful partner, enabling humanity to tackle grand challenges and unlock new potentials.
Okay, this is fascinating and maybe a little daunting. Let's shift gears slightly and dig into the theoretical foundations. What are the core ideas underpinning this whole AGI endeavor?
It really starts with the concept of intelligence itself, which is surprisingly slippery. Despite centuries of philosophy and psychology, there's still no single, universally accepted definition of what intelligence is.
So we're trying to build something we can't perfectly define. That seems challenging.
It is. But for the purposes of AGI research, we usually focus on a collection of capabilities. Things like abstract reasoning, complex problem solving, learning efficiently from experience, acquiring and applying knowledge, recognizing subtle patterns, adapting behavior effectively across diverse environments, all without task-specific programming for each new challenge.
And are there different angles to approach understanding intelligence?
Definitely. You can look at it computationally, intelligence as information processing, algorithms, computation, or biologically, how does intelligence arise from neural structures, from evolution? Psychologically, what are the cognitive processes involved? How does intelligence develop in humans? And philosophically, tackling the deep questions about consciousness, intentionality, the nature of mind.
It really takes input from everywhere.
Absolutely. You need all those perspectives. And even within psychology, you have theories that challenge a single G factor or IQ score view. Think of Howard Gardner's multiple intelligences, musical, spatial, interpersonal, etc., or Sternberg's triarchic theory, analytical, creative, practical intelligence. These remind us that intelligence isn't monolithic.
How do these broader theories feed into actually building AGI?
Certain theoretical frameworks are particularly relevant. For example, predictive processing theories, like Carl Friston's free energy principle, suggest that intelligence is fundamentally about predicting the world and minimizing surprise or prediction error. Hierarchical learning models are important for understanding how we build complex concepts from simpler ones. And Judea Pearl's work on causality is crucial because reasoning about cause and effect, not just correlation, is vital for true understanding and planning, something current AI often lacks.
You mentioned philosophy earlier, the mind-body problem. How do different philosophical stances impact AGI thinking?
They have huge implications. If you're a Cartesian dualist, believing mind is non-physical, then maybe true AGI consciousness is impossible computationally. If you're a materialist, believing mind is physical brain activity, then machine consciousness seems at least possible in principle. Functionalism is very influential in AI. It says mental states are defined by their functional role, their inputs and outputs, not what they're made of. So if you build a system with the right functional organization, maybe consciousness could emerge, whether it's biological or silicon.
So functionalism is more optimistic about AGI consciousness?
Generally, yes. It opens the door conceptually. Then you have more exotic views like panpsychism, the idea that consciousness is a fundamental property of matter itself, which has different implications again.
And what about specific theories of consciousness? Are researchers trying to model those?
Some are, yes. Theories like Bernard Barr's global workspace theory, which suggests consciousness acts like a central blackboard where different brain processes can share information, have directly inspired computational architectures like life. There's also integrated information theory, IIT, from Giulio Tononi, which links consciousness to the complexity of information integration in a system, and even proposes a mathematical measure, phi. And higher order theories propose consciousness involves having thoughts about our own mental states, a kind of self-reflection.
So still lots of different ideas floating around about consciousness itself.
Absolutely. And the big unanswered question remains. What's the precise relationship between intelligence and consciousness? Do you need subjective experience, phenomenal consciousness as philosophers call it, for general intelligence?
Can you have one without the other?
That's the debate. Some, like John Searle, argue yes, you need real subjective awareness. Others, like Daniel Dennett, argue you can achieve all the functional aspects of intelligence without genuine what-it's-like consciousness. Developing AGI might actually give us empirical ways to test some of these ideas.
Okay, let's talk about the computational models. You mentioned symbolic AI and connectionism earlier. Can you elaborate on those cognitive models?
Sure. Symbolic AI, or classical AI, represents knowledge explicitly using symbols and manipulates them using logical rules. Think Newell and Simon's physical symbol system hypothesis, the idea that intelligence is symbol manipulation. This approach excels at formal reasoning, planning, knowledge-based tasks.
But its limitations led to AI winters, right?
Exactly. The struggle with perception, learning from noisy data, ambiguity, the messiness of the real world. Connectionism, on the other hand, inspired by neural networks in the brain, uses interconnected nodes, or neurons. It excels at learning patterns from data, perception, classification tasks symbolic AI found hard.
So the deep learning approach.
Right. Deep learning is a modern form of connectionism. But pure connectionist models often struggle with high-level abstract reasoning, systematic planning, and incorporating explicit knowledge easily.
So each has strengths and weaknesses.
Precisely, which is why there's so much interest now in hybrid models, trying to combine the pattern recognition power of neural networks with the structured reasoning and knowledge handling of symbolic systems. Think neurosymbolic AI.
Best of both worlds.
That's the goal. Cognitive architectures like Clarion, for instance, explicitly try to implement dual-process theories from psychology, having both fast, intuitive, connectionist-like systems and slower, deliberate, symbolic-like systems. Probabilistic programming also tries to blend statistical learning with structured logical representations.
So what are the key ingredients for a successful AGI cognitive architecture?
It would likely need several components working together. Multiple memory systems, sensory buffers, working memory, long-term episodic experiences, and semantic facts, memory, procedural memory skills.
It's the different ways we remember things.
Exactly. And diverse learning mechanisms, supervised, unsupervised, reinforcement learning, but also maybe one-shot learning, learning from a single example, and meta-learning, learning how to learn. Plus flexible reasoning processes, deduction, induction, abduction, inference to the best explanation, analogy, causal reasoning.
It's putting all those pieces together in one system.
Right. It's unlikely that AGI will come from just one narrow tradition. It will probably incorporate elements from symbolic, connectionist, and perhaps other approaches yet to be discovered.
We've touched on the limitations of current narrow AI, but let's revisit that comparison now, focusing specifically on why today's impressive AI still falls short of AGI.
Right. Even with systems like GPT-4 or multimodal models that handle text and images, which seem incredibly capable, there are still fundamental gaps separating them from true general intelligence.
What are the absolute key distinctions?
Okay, number one is robust generalization. Current AI often fails when presented with data or situations that are even moderately different from its training data, what we call out-of-distribution examples. It lacks resilience to novelty.
It's brittle.
In many ways, yes.
Yeah.
Second, transfer learning. While there's progress, applying knowledge learned in one domain, say medical imaging, to a fundamentally different domain, like financial prediction, without extensive retraining remains a huge challenge. Humans do this naturally. AI struggles.
Okay, generalization and transfer. What else?
Common sense reasoning. This is a massive one. AI lacks the vast reservoir of background knowledge about how the physical and social world works that humans absorb implicitly from experience. Things like water makes things wet. You can't push something with a rope. Basic causality. They have to be painstakingly programmed or somehow inferred, which is incredibly hard.
So they lack basic world knowledge.
Fundamentally, yes.
Yeah.
Which also relates to cross-domain transfer. Even if two problems share an underlying logical structure but are in different fields, AI often can't recognize or leverage that similarity. It needs retraining.
What about understanding, really understanding?
That's another core difference. Current AI, even sophisticated language models, manipulate symbols based on statistical correlations, but there's little evidence they possess genuine comprehension of the underlying concepts those symbols represent.
And adaptability, learning on the fly.
It's limited. They typically require offline retraining on large data sets. Their capacity to learn incrementally from new experiences in real time and dynamically adjust their strategies is still quite primitive compared to humans or even animals. And finally, goal formulation. Current AI systems pursue goals given to them by programmers. They don't generally formulate their own intrinsic goals and motivations.
But research is trying to tackle these limitations, right? You mentioned neurosymbolic AI.
Absolutely. That's a major thrust, combining neural learning with symbolic reasoning structures. Cognitive architectures are another approach, trying to build systems with more human-like memory and learning components. Embodied AI is crucial too, the idea that intelligence needs to be grounded in physical interaction with the world to develop real understanding and common sense.
Learning by doing.
Exactly. And there's research into autotelic AI, or intrinsically motivated systems, that explore and learn out of curiosity, setting their own goals in an open-ended way. These are all potential avenues toward bridging the gap.
Let's revisit those potential applications we discussed earlier. Science, healthcare, education. How would AGI specifically go beyond what narrow AI can achieve in those areas?
Okay, take scientific research. Narrow AI might be great for analyzing a specific experimental data set or simulating a known protein structure. An AGI, however, could potentially function as that autonomous scientist we talked about, identifying novel research questions across disciplines, designing entirely new experimental paradigms, making conceptual leaps that integrate knowledge from physics, biology, chemistry, etc., to tackle something like fusion energy or quantum gravity.
A whole different level of contribution.
Completely. In healthcare, narrow AI might detect diabetic retinopathy from eye scans. AGI could manage a patient's entire health journey across their lifespan, integrating genomic data, real-time sensor readings, environmental exposures, patient preferences, and the latest medical literature to create dynamically evolving, deeply personalized health strategies. It's holistic care versus task-specific assistance.
And education, beyond just delivering content.
Right. Current AI tutors might help with math problems within a fixed curriculum. An AGI tutor could develop a rich cognitive model of the individual student, their knowledge, misconceptions, learning style, even motivational state. It could engage in deep Socratic dialogue, foster metacognitive skills, learning how to learn, provide emotional encouragement, and weave together concepts across subjects, adapting constantly.
So it's the integration, adaptability, and deeper understanding that really separates AGI's potential impact from narrow AIs.
Precisely. AGI isn't just about doing current tasks better. It's about enabling fundamentally new capabilities through the synergistic integration of perception, reasoning, learning, memory, and action. This could lead to entirely new applications in scientific fields we can't even conceive of today, stemming from these emergent functionalities.
And the path there is likely this gradual expansion and integration of capabilities we see hints of now.
That seems the most plausible route. Trends like multimodal models, handling text, image, audio, large foundation models with surprising emergent abilities, and meta-learning are steps along that path. But, and this is key, significant conceptual and technical breakthroughs are still needed. It's likely a progressive expansion, not flipping a switch.
Okay, this provides a great foundation. Now, let's get into the nuts and bolts. What are the main technical approaches researchers are actually using to try and build AGI, starting perhaps with machine learning and deep learning?
Right, so AGI really pushes the frontiers of computation. And machine learning, especially deep learning, has become arguably the dominant approach, or at least a central component in recent years. The core idea of machine learning, remember, is systems learning from data, rather than being explicitly programmed with rules for every scenario. That ability to generalize from data is seen as crucial for general intelligence.
We hear terms like supervised, unsupervised, reinforcement learning thrown around a lot. Can you break those down in the context of AGI?
Sure. Supervised learning is where we train a model on data that's already labeled with the right answers. Input.picture, label.cat. The model learns a mapping from inputs to outputs by minimizing the difference between its predictions and the known labels. using a loss function.
Like learning with flashcards.
Kind of, yeah. Decision trees, support vector machines, and especially deep neural networks have had huge success with this. But the big limitations are the need for vast amounts of labeled data, which is expensive and time-consuming to create, and the fact it often assumes the test data will look like the training data, the closed-world assumption. That's not how humans primarily learn.
We learn by observing, mostly without explicit labels.
Exactly, which leads to unsupervised learning.
Hmm.
Here the model gets unlabeled data and has to find structure or patterns on its own. Think clustering similar data points, reducing data dimensionality, or learning to generate new data similar to the input, like with VAEs, GANs, or autoregressive models like GPT.
This sounds much closer to AGI's needs, leveraging unlabeled data.
It's definitely seen as crucial. It aligns better with how humans learn through observation, lets us use the enormous amount of unlabeled data out there, and can potentially discover novel patterns we didn't even know existed. The challenges are evaluating performance without ground truth, and the fact that models often need to make assumptions about the data's underlying structure.
And where do semi-supervised and self-supervised fit in?
They try to bridge the gap.
Yeah.
Semi-supervised uses a little bit of labeled data alongside a lot of unlabeled data. Self-supervised learning has become incredibly important, especially for foundation models. Here, you create surrogate tasks from the unlabeled data itself, like masking words in a sentence and training the model to predict them, or predicting the next frame in a video. It massively reduces the need for manual labels.
Okay, and reinforcement learning, how does that contribute?
Reinforcement learning, RL, is about learning through interaction and feedback. An agent takes actions in an environment, receives rewards or penalties, and learns a policy, a strategy, to maximize its cumulative reward over time. Think AlphaGo, learning to play Go, or robots learning to walk.
Learning by trial and error.
Essentially, yes, it's powerful for decision-making tasks. But challenges include designing good reward functions. Defining good performance can be hard for complex tasks. And the credit assignment problem, figuring out which actions led to a reward that came much later.
It feels like human intelligence uses all of these, right? Instruction, observation, trial and error.
Absolutely. And that's a key insight for AGI research. A truly general intelligence will likely need to integrate and flexibly deploy all these learning paradigms, just like we do.
Let's talk deep learning architectures. What are the fundamental building blocks?
Okay, at the base are artificial neurons, simple processing units organized in layers. Each neuron takes inputs, computes a weighted sum, applies an activation function, introducing nonlinearity, and passes the output to the next layer.
And deep just means lots of layers.
Exactly. Feed-forward networks are the simplest type. The universal approximation theorem tells us even a single hidden layer network can approximate any continuous function. But deep networks, many layers, are often much more efficient at learning complex patterns. They enable hierarchical representation learning. Early layers learn simple features, edges, textures. Later layers combine these into more complex concepts, objects, scenes.
Are there specialized architectures for different kinds of data?
Yes, definitely. Convolutional neural networks, CNNs, are dominant for grid-like data, especially images, using filters to detect spatial patterns. Recurrent neural networks, RNNs, including LSTMs and GRUs, are designed for sequential data like text or time series, having internal memory to process sequences.
And transformers. They seem to be everywhere now.
Transformers revolutionize sequence modeling, particularly NLP. They use a mechanism called self-attention to weigh the importance of different input elements when processing any given element, allowing them to capture long-range dependencies efficiently and enabling parallel computation, which made training huge models feasible. Then you have graph neural networks, GNNs, for data structured as graphs, learning from relationships between entities.
How do these complex networks actually learn? The training process.
It's primarily through backpropagation, an algorithm that efficiently calculates how much each connection weight in the network contributed to the overall error in the output. Then, optimization algorithms like stochastic gradient descent, SGD, adjust those weights slightly in the direction that reduces the error.
Nudging the weights towards the right values.
Exactly. There are many refinements like momentum or adaptive learning rates, Atom Optimize is very popular, to navigate the incredibly complex, non-convex loss landscape of these huge networks more effectively. It's about finding a good minimum in that landscape.
But you mentioned scaling alone isn't enough for AGI. What are the limitations even with these powerful architectures?
Right. Despite their successes, large models still struggle with robust causal reasoning, long-term planning, factual consistency, alignment with human intent, and they can be brittle or vulnerable to adversarial attacks. Just making them bigger doesn't automatically fix these issues. Architectural innovations and integrating them with other approaches seem necessary.
Are there other, perhaps less mainstream neural network ideas being explored?
Yes. Spiking neural networks, SNNs, try to model brain dynamics more closely using discrete spikes, potentially offering energy efficiency advantages. Neuroevolution uses evolutionary algorithms to optimize network architectures and weights. Energy-based models, EBNs, define probabilities implicitly through an energy function, offering unifying perspective. Bayesian neural networks, BNNs, aim to quantify uncertainty in predictions, which is crucial for robust decision-making.
So the path forward likely involves mixing and matching, combining deep learning strengths with other ideas.
That seems to be the consensus. Integrating deep learning's power in perception and pattern recognition with more structured approaches for reasoning, planning, and knowledge handling is probably the most promising direction towards AGI.
Okay, that's a great overview of the machine learning side. Now let's switch to those other approaches you mentioned, symbolic reasoning and knowledge representation. How do these classical AI methods fit into the AGI picture?
Right. While deep learning dominates headlines now, symbolic AI offers crucial complementary strengths. It excels at systematic, logical reasoning, provides inherent interpretability. You can often trace the steps of its reasoning, and it's designed for integrating explicit knowledge in structured ways.
So it's more about rules and logic than pattern matching.
Exactly. Foundational systems include propositional logic, dealing with true-false statements and connectives like AND or not AT, and, more powerfully, first-order logic, FOL. FOL lets us represent objects, their properties, and relationships between them using predicates and quantifiers for all there exists.
Like representing all humans are mortal.
Precisely. FOL hits a sweet spot between expressiveness and computational manageability, making it a cornerstone of knowledge representation. We can then use automated theorem-proving techniques, algorithms like resolution or tableau methods, to derive new logical consequences from known facts and rules. This is used in areas like software verification.
But the real world isn't always black and white, true or false. How does symbolic AI handle uncertainty or exceptions?
That's a critical point. Classical logic struggles there. So researchers developed non-monotonic logics like default logic, birds typically fly, allowing exceptions like penguins, or circumscription, assuming things are as expected unless stated otherwise.
Making assumptions you can retract.
Right. And also probabilistic logics. Things like Markov logic networks, MLNs, combine FOL with probabilistic graphical models, allowing weighted roles and reasoning with uncertainty. Bayesian logic programming does something similar, integrating logic programming with Bayesian networks.
What about logic programming itself, like Prolog?
Logic programming represents knowledge as logical clauses and uses inference mechanisms like backward chaining to answer queries. It was foundational for many early expert systems and still has applications in areas like natural language processing. Constraint satisfaction problems, CSPs, are another symbolic technique defining problems in terms of variables, domains, and constraints, used widely in scheduling and resource allocation. Answer set programming, ASP, is yet another powerful formalism for complex combinatorial problems and common sense reasoning.
So lots of different formalisms for structured reasoning. What are the big advantages?
Yeah.
And the downsides?
Advantages are clear. Transparent reasoning steps, potential for formal verification, easy integration with existing knowledge bases. The struggles are often with handling perception directly, dealing gracefully with massive uncertainty or ambiguity, and the difficulty of acquiring the necessary knowledge automatically on a large scale, the knowledge acquisition bottleneck.
How do we structure all this knowledge? You mentioned FOL, but how do we organize concepts?
That's where ontologies and semantic networks come in. An ontology is a formal, explicit specification of a shared conceptualization, basically, defining the concepts, properties, relationships, and axioms within a domain. Think of creating a structured vocabulary for both humans and machines.
Like defining what a mammal is and its relation to animal.
Exactly. Languages like OWL and RDF are used to build these. Large projects like Psych, for common sense, the gene ontology biology, or WordNet language, are examples. Ontologies enable explicit knowledge sharing, integration, and sophisticated reasoning. The downside is they often require significant human effort to create and maintain, and can be rigid.
And semantic networks.
Semantic networks are simpler graph structures, where nodes represent concepts or entities and edges represent relationships, like this is a Haspart. They focus more on associative connections, enabling reasoning by traversing the graph. Frames extend this idea, providing structured slots for attributes within concepts, supporting defaults and inheritance.
I've heard of knowledge graphs. How do they relate?
Modern knowledge graphs, like Google's Wikidata YAGO, essentially combine ideas from semantic networks, frames, and ontologies at massive scale. They store billions of facts and relationships, powering search engines, question answering, etc., but ensuring their completeness and consistency is a huge challenge.
Are there other ways knowledge has been represented symbolically?
Yes, early work included things like conceptual dependency, CD theory, which try to represent meaning using a small set of primitive actions, like transfer possession, forgive. Scripts extended this to represent stereotypical event sequences, like the steps involved in dining at a restaurant, allowing inference of implied details.
Like knowing you'll probably get a menu.
Exactly. But these struggled with novel situations outside the script. A huge ongoing challenge is capturing common sense knowledge, the vast amount of implicit understanding we have about the everyday world. Projects like ConceptNet, Atomic, Inferential Knowledge, and Visual Genome, linking language to vision, are trying to build these common sense knowledge bases, but the sheer scale and implicit nature make it incredibly difficult.
It really highlights the complementary nature. Symbolic AI is great for structure and reasoning, but struggles with perception and fuzziness. Neural nets are great for perception and patterns, but struggle with reasoning and structure.
Precisely. Which leads us directly to the need for integration.
Exactly. So let's talk about integrating these two worlds, symbolic reasoning and subsymbolic machine learning. Why is this seen as such a critical path towards AGI?
Well, as we just discussed, each paradigm has fundamental limitations. Neural nets excel at perception and learning from raw, messy data, but often lack interpretability and struggle with systematic reasoning or easily incorporating prior knowledge. Symbolic systems are great for reasoning, planning, and knowledge integration, but brittle with noisy data and poor at learning from scratch.
So the idea is to get the best of both worlds.
Precisely. Combine the perceptual power and learning ability of neural networks with the reasoning, abstraction, and knowledge handling capabilities of symbolic systems. There's even inspiration from neuroscience here. The complementary learning systems theory suggests our brain uses different systems, like the hippocampus for rapid learning of specifics and the neocortex for slower generalization, that work together.
Makes sense. What are the main ways researchers are trying to combine them?
There are several strategies. Simple pipeline architectures are common. Maybe a neural network processes an image to identify objects and then passes that symbolic description to a classical planner.
One feeds the other.
Right. More integrated approaches include neurosymbolic embeddings. This involves representing symbolic structures like entities and relations in a knowledge graph, or even logical rules within the continuous vector spaces used by neural networks. This allows the network to learn while respecting or utilizing that symbolic structure.
Embedding logic within the network itself?
Kind of, yeah. Another approach is neuralized symbolic processors, where you essentially implement symbolic operations, like logical inference or program execution, using differentiable neural network components. This allows the entire system, including the symbolic reasoning part, to be trained end-to-end using standard deep learning techniques like backpropagation.
Can you give some examples of systems that actually do this?
Sure. AlphaGo and AlphaZero are classic examples. They use deep neural networks for pattern recognition, evaluating Go board positions and suggesting moves, but combine that with a symbolic Monte Carlo tree search algorithm for structured planning and exploring future possibilities. That synergy was key to their superhuman performance.
So neural intuition guiding symbolic search.
Exactly. Another example is IBM's Neurosymbolic Concept Learner. It uses neural nets for vision and language parsing, translates the language into a symbolic program, and then executes that program against the symbolic representation of the scene to answer visual questions. This approach showed better data efficiency and interpretability.
Interesting. Any others?
AI2's Aristo system for science question answering combines multiple solvers, some based on large language models, subsymbolic, others querying knowledge bases, symbolic, others analyzing diagrams, and uses a meta-solver to pick the best approach. Meta AI's data-to-text systems use symbolic planning to select key information from structured data before feeding it to a neural network to generate a fluent natural language summary.
It seems like these hybrid systems offer real advantages then.
The potential benefits are huge. Enhanced reasoning capabilities beyond pure neural nets, better interpretability because the symbolic parts are often understandable, improved robustness, potentially better data efficiency because you can inject prior knowledge symbolically, and better generalization.
But it's not easy to just stick them together, I imagine.
No, definitely not. There are significant technical challenges. How do you design the interface between the neural and symbolic parts? How does uncertainty flow between them? How do you train them together? Effectively getting gradients to flow through symbolic components can be tricky. How do you ground the symbols used by the reasoning part in the messy perceptual data processed by the neural part? These are active research areas.
What are the exciting future directions in this neurosymbolic space?
Developing more fully end-to-end differentiable architectures is a major goal. Deeper integration within large foundation models is another, maybe augmenting them with symbolic reasoning modules or using symbolic knowledge to guide their fine-tuning or prompting. Meta-learning techniques that allow a system to learn which combination of neural and symbolic approaches works best for a given task are also very promising.
So neurosymbolic integration really feels like a core strategy for AGI.
I think many researchers would agree it directly addresses the complementary weaknesses of the two dominant paradigms in AI history. By finding ways to effectively combine deep learning strengths with symbolic AI strengths, we stand a much better chance of building systems that possess the kind of flexible, robust, general intelligence we're aiming for with AGI. It's about bridging that gap.
This brings us to a really critical area, the ethical considerations and societal impact of AGI. If we succeed or even make significant progress, the consequences are enormous. Where do we even start untangling the ethics?
It's incredibly complex and touches almost every aspect of society. A good starting point is more responsibility and accountability. If an autonomous AGI system makes a decision that causes harm, who is responsible?
The programmer, the user, the company that built it, the AI itself.
Exactly. Traditional frameworks break down. AGI might develop emergent behaviors its creators didn't intend or foresee. Responsibility gets diffused across developers, deployers, users, corporations, regulators. It's a thorny issue. Practical approaches involve building in traceability, explainable AI, XAI methods, maybe formal verification, but these have limitations, especially with highly complex or self-modifying systems.
Self-modifying systems, that adds another layer entirely.
It really does. It potentially breaks the chain of human responsibility. We also need institutional frameworks, independent oversight bodies, whistleblower protections, perhaps specific liability rules or insurance requirements. International coordination is vital here too.
Okay, accountability is huge. What about fairness and bias? We already see issues with narrow AI.
AGI could amplify those problems massively. AI systems learn from data, and if that data reflects existing societal biases, racial, gender, socioeconomic, the AI will learn and potentially perpetuate or even worsen those biases.
How can bias creep in?
In many ways. Representational harms, from skewed data underrepresenting certain groups. Measurement harms, where the metrics used to evaluate the AI overlook negative impacts on marginalized communities. Allocational harms, where the AI unfairly distributes resources or opportunities, think loan applications, hiring, even criminal justice risk assessments. Sometimes it's subtle, through proxy discrimination, using seemingly neutral variables.
And there's no easy technical fix, right? I've heard about fairness and possibility theorems.
Correct. Often, different mathematical definitions of fairness are mutually incompatible. You have to make value judgments about which dimensions of equity to prioritize, which is inherently a societal and political choice, not just technical. And deploying AGI globally means navigating incredibly diverse cultural values while upholding fundamental human rights, a huge balancing act.
So what can be done?
Technical approaches help. Diversifying training data, building fairness constraints into algorithms, adversarial debiasing, causal modeling to understand bias mechanisms, multi-stakeholder optimization. But it also requires independent audits, continuous monitoring after deployment, and strong governance frameworks. It's an ongoing process, not a one-time fix.
Let's talk economics. The future of work seems like a massive area of concern.
It is. AGI automation could be different from past waves because its scope might extend far beyond routine tasks into complex cognitive domains, potentially impacting doctors, lawyers, scientists, artists, high-status professional roles.
So not just blue-collar or low-level white-collar jobs.
Potentially, yes. And the impacts won't be uniform. Certain sectors and demographics might be hit harder, potentially worsening existing inequalities. We could see geographical disparities intensify, with wealth concentrating where AGI is developed and deployed, potentially leaving developing economies further behind.
What are the deeper structural economic changes we might see?
Things like a shift in the balance between labor income and capital income, with capital, owners of AGI, capturing more value. Concentration of AGI ownership could lead to extreme wealth inequality. The fundamental link between human labor and economic value could weaken.
What are the potential policy responses being discussed? UBI.
Universal basic income is definitely one. Job guarantee programs are another. Massive investment in reskilling and lifelong learning. Exploring worker ownership models for AI systems. Progressive taxation on capital or AGI-driven profits. Each has trade-offs and huge implementation challenges. The transition period itself could be incredibly disruptive for individuals and communities. And we shouldn't forget the psychological and social importance of work beyond just income.
It sounds like we need proactive policies before mass displacement happens.
Ideally, yes. Waiting until millions are unemployed is too late. But the political will and foresight are challenging. Managed thoughtfully, AGI could usher in an era of abundance, but we need deliberate effort to ensure benefits are distributed equitably.
Let's pivot to some potentially positive impacts. Healthcare and education enhancements.
Absolutely. In healthcare, AGI could revolutionize diagnosis by integrating complex multimodal data for earlier, more accurate detection. Personalized treatment planning, as we discussed, enhanced delivery through continuous monitoring, virtual assistance, maybe even robotic surgery with superhuman precision. It could dramatically improve access and quality, potentially addressing healthcare worker shortages.
And education.
Truly personalized learning tailored to each individual's needs. Advanced AI tutoring, providing customized feedback. Transforming pedagogy itself by allowing deeper understanding of how students learn. The potential for democratizing high-quality education is immense.
But there are concerns here too, surely. Privacy, the human element.
Big concerns. Healthcare AGI requires access to vast amounts of incredibly sensitive data. Privacy is paramount. Autonomy is another issue, finding the right balance between algorithmic guidance and human judgment, both for doctors and patients. And crucially, ensuring AI complements rather than replaces the essential human connection in care and teaching.
Implementation is also tricky.
Yes. Integrating with existing hospital systems, potential resistance from professionals, ensuring quality and safety, addressing equity so these benefits don't just accrue to the wealthy. It requires careful, multidisciplinary development and deployment.
This all screams the need for regulation and governance. What's the current state of play, and where might we need to go?
The current legal landscape is fragmented, inconsistent, and largely inadequate for the unique challenges AGI poses. Existing laws weren't designed for autonomous, learning, potentially unpredictable systems.
Can you give some examples?
Data protection laws like GDPR are relevant, but vary globally. Product safety and liability frameworks, like the EU AI Act is starting to address, struggle with AI. How do you determine fault when a learning system causes harm? Who is liable? Novel approaches might be needed. Sector-specific rules exist, usually for medical devices, but AGI blurs boundaries. Intellectual property law is grappling with AI-generated works. Current systems often require a human inventor author. National security and export controls are increasingly targeting AI.
So we need AGI-specific regulations.
Very likely. Approaches that address autonomy, complexity, emergent behavior, and are grounded in broader human values, not just technical specs. Potential novel governance approaches include risk-based regulation, like the EU AI Act, but needing to be more dynamic for AGI, pre-deployment assessments, impact assessments, conformity checks, mandatory transparency and explainability where feasible, dedicated oversight bodies, like an FDA for AI, technical safeguards developed through alignment research, anticipatory governance using foresight and scenario planning, and crucially, international cooperation despite geopolitical hurdles.
What are the key challenges in designing this governance?
Balancing innovation with risk management, the sheer pace of AI development outstripping the speed of regulation. Pacing problem. Figuring out the right timing for intervention. Too early stifles innovation, too late allows harms to occur. It's a wicked problem requiring technical, institutional, and legal mechanisms working together.
Okay, let's shift focus slightly to the research landscape itself. Who are the key players pushing AGI research forward?
It's a mix of academia, industry labs, national initiatives, and collaborative efforts. In academia, you have major centers like MIT, CSAIL, Media Lab, Stanford, SAIL, HAI, Carnegie Mellon, SCS, UC Berkeley, CHAI focusing on safety, Oxford Future Humanity Institute, University of Edinburgh, and many others, often focusing on foundational research, specific capabilities, or ethical considerations.
And the big tech companies are obviously heavily involved.
Hugely. Google, including DeepMind, has been a leader with breakthroughs like AlphaGo and now models like Gemini, plus significant AI safety research. OpenAI, with its GPT series, DALL-E, and focus on alignment, has driven much public attention. Meta AI, Facebook contributes significantly, often through open research like Llama. Microsoft Research has deep expertise and integrates AI across its products, often partnering with OpenAI. And NVIDIA provides the crucial hardware backbone enabling much of the deep learning progress.
Are governments stepping up with national strategies?
Yes, increasingly. The UK has its AI strategy, the AI Research Resource, and the Alan Turing Institute. China has its new generation AI development plan, and major labs like BAAI. The EU funds research through programs like Horizon Europe and initiatives like CLARE. Japan has RIKEN AIP. Many countries see AI, including the path to AGI, as strategically vital.
Is there much international collaboration happening?
There are efforts. Organizations like the Partnership on AI, Industry, Academia, Civil Society, the Global Partnership on AI, GPAI, government level, the OECD AI Policy Observatory, and the UN's AI Advisory Body aim to foster dialogue, research collaboration, and policy coordination on AI governance and ethics. There are also decentralized open-source efforts like Eleuther AI and Theminal Collective working on accessible models and research.
So a complex ecosystem of competition and collaboration.
Exactly. While there's intense competition, there's also a growing recognition that the biggest challenges of AGI, particularly safety and ethics, require broad cooperation across organizations and nations.
Looking at the research itself, what are some of the most exciting recent breakthroughs, and what are the biggest hurdles that still remain?
There has been genuinely remarkable progress recently. One huge area is foundation models, like large language models and multimodal models. The surprising emerging capabilities they exhibit when trained at massive scale, things like in-context learning, basic reasoning, coding ability, were not explicitly programmed, but arose from the scale.
Abilities they weren't specifically trained for.
Right. Also, improvements in zero-shot and few-shot learning, where models can perform tasks with little or no specific training examples for that task, suggesting some degree of knowledge transfer. We're seeing AI make real contributions in science, like AlphaFold revolutionizing protein structure prediction, and in creativity with image-video generation, DALE, Sora, and music generation. Autonomous agents like AutoGPT showed glimpses of systems pursuing complex goals, and there's progress, albeit debated, in areas like theory of mind and LLMs, meta-learning, causal reasoning, and intrinsic motivation.
So definite steps forward. But what are the major roadblocks still standing in the way of true AGI?
Despite the progress, significant gaps remain. Robust generalization is still a huge one, making AI reliable outside its training distribution in truly novel, unexpected situations. Causality and common sense, deep understanding of cause and effect, and basic world knowledge is still lacking. Planning and long-term reasoning towards complex, multi-step goals remains very challenging for current architectures.
Memory limitations, too.
Yes. Effective mechanisms for storing, retrieving, and integrating diverse experiences over long timescales are still underdeveloped compared to human memory. There's also the fundamental challenge of balancing specialization and generalization. How do you build a system that can be both expert in specific domains and broadly adaptable? The integration of symbolic and subsymbolic methods, as we discussed, is still an active research challenge. And of course, the profound philosophical and ethical questions around consciousness, sentience, and alignment remain largely unresolved.
What are some emerging trends or technologies that might help tackle these challenges?
Architecturally, things like modular approaches, for example, mixture of experts, show promise. Continued focus on neurosymbolic methods for reasoning and planning. Better evaluation benchmarks that go beyond static datasets to interactive environments are crucial. Integrating safety and alignment research during capabilities development, not just after. Technically, over the next decade, we might expect deeper multimodal integration, more robust causal inference methods, and significant advances in reasoning and planning components.
And how might this translate into applications in society in, say, the next 10 years?
We'll likely see AI making even more substantial contributions in scientific research, expanding into more complex healthcare roles beyond simple diagnosis, and starting to have more noticeable impacts on education and the workforce, requiring adaptation. Social and emotional intelligence in AI will likely advance, but probably remain quite limited compared to humans.
So significant progress likely, but true AGI still seems further out.
That's the general view. True human-level general intelligence across the board remains a distant goal. But the pace of progress is rapid, and the focus on alignment, responsible deployment, and governance will only intensify as capabilities increase.
As we look towards the future of AGI, wrapping things up, what are the key takeaways or themes we should keep in mind?
I think it's clear AGI represents a potential inflection point for humanity, demanding proactive thought and governance. Key themes that emerge are The central challenge of alignment, ensuring these powerful systems remain beneficial and aligned with human values. The sheer transformative potential across literally every sector of society. The absolute necessity of embedding safety and ethical considerations from the very beginning. And the critical importance of developing robust, adaptive governance frameworks nationally and internationally.
What might capabilities look like beyond the next decade if development continues?
We're entering more speculative territory, but possibilities include systems capable of very long-horizon planning and strategy, much more rapid and widespread deployment across the economy, safety and alignment becoming even more central research pillars, perhaps the emergence of global governance frameworks, significant economic transformation, potentially accelerating scientific and technological discovery at an unprecedented rate, maybe even direct human cognitive enhancement through brain-computer interfaces. And of course, the possibility of reaching AGI and potentially moving towards superintelligence.
Which brings up various future scenarios people discuss.
Right. From positive scenarios of human-AI integration and augmentation, maybe even speculative biological-digital convergence, to more cautionary or even existential risk scenarios if alignment fails or control is lost. It's a vast range of possibilities.
What technical directions might enable these future capabilities?
Continued development of hybrid cognitive architectures. Perhaps breakthroughs in self-improving systems. Recursive self-improvement is a key concept here. Hardware innovations like neuromorphic computing, brain-inspired chips, could be important. And maybe even entirely new paradigms like quantum computing or biological or molecular computation, though those are further out. A constant focus will be on creating trustworthy AI systems that are reliable, safe, secure, private, transparent, explainable, and behave predictably.
You mentioned human-AI collaboration earlier. How might that look in practice?
The idea is to leverage complementary strengths. Humans excel at creativity, common sense, ethical judgment, deep understanding. AGI might excel at processing vast data, complex calculations, tireless operation. So you could have centaur systems where humans provide strategy and goals, AI handles tactics and execution. Co-pilot models where AI acts as an intelligent assistant. Critique partnerships where AI reviews or challenges human work. Even teachable agents where AI learns rapidly from human interaction.
And the interfaces for this collaboration would need to evolve.
Absolutely. We'd need much richer interaction, multimodal, voice, gesture, gaze, adaptive personalization, maybe AI systems aware of the human's cognitive state, allowing for seamless mixed initiative interaction where control flows naturally between human and AI. Human-AGI collaboration could become a dominant paradigm for work and creativity.
So what is the role of humans in a world with AGI? Are we just supervisors?
It's a huge question. Partnership models suggest active roles. Specialization might occur, focusing on uniquely human skills, complex social interaction, emotional intelligence, ethical deliberation, creativity, physical dexterity, perhaps. The care economy might expand. Education becomes critical.
How does education need to change to prepare for this future?
Fundamentally, we'll need skills for interacting effectively with AI, but also doubling down on uniquely human capabilities AI struggles with. Adaptability, critical thinking, technological discernment, understanding AI's limits and biases become paramount. Educational systems themselves could be transformed by AI, offering personalized, lifelong learning pathways. The focus needs to shift beyond just job training to fostering resilience, agency, and the ability to shape how AI is integrated into society ethically. Preparing for uncertainty is key.
This has been an incredibly comprehensive journey through the world of AGI. We've covered its definition, how it differs from narrow AI, its deep historical roots, the complex theories involved, the transformative potential, the immense ethical stakes, the research landscape, breakthroughs, challenges, and potential futures.
It really touches on so many fields and raises fundamental questions about intelligence, consciousness, and humanity's future.
Understanding AGI isn't just for tech specialists anymore. It feels essential for everyone navigating the coming decades. Thank you so much for breaking it all down for us.
It was my pleasure. It's a fascinating and incredibly important topic to discuss.
And thank you all for joining us on this deep dive.
We hope this exploration has given you valuable insights into artificial general intelligence.
As a final thought to leave you with, considering the immense potential for both unprecedented progress and unforeseen challenges, what single principle do you believe should be most paramount in guiding the development and deployment of AGI? Something to ponder.
Keep exploring, keep questioning. This field is evolving incredibly quickly.
Thanks again for tuning in to this deep dive.